Welcome, everybody, to the Thoughtworks Technology Podcast. I'm going to be the host today. My name is Scott Shaw, and I'm joined today with co-host Rebecca Parsons. Would you like to introduce yourself, Rebecca?
Hello, everyone. This is Rebecca Parsons, another one of your regular co-hosts. I'm the CTO Emerita, and we are joined today by another thought worker based in India who has just written a book. Or finished a book. Unmesh, would you like to introduce yourself?
Hi everyone. I'm a principal consultant at Thoughtworks and been with Thoughtworks for close to 16 years now. And as Rebecca said, had been involved in writing about distributed systems for the last few years, which is now compiled into a book, which is out.
Yeah, and that's quite an accomplishment. Unmesh and I worked together 10 years ago or more back in Pune, India. So it's a pleasure to be talking to you again. So the book is called Patterns of Distributed Systems, which is a pretty big topic. And I think it's also something that's probably not that well documented elsewhere. And so I think this is a unique book and probably fills a needed gap that in the market right now. But I wonder, how was it that you first came to want to write a book? How did this get started initially?
Yeah, I mean, it's a long journey. I think it started back in 2015-16. I mean, when some questions started coming to my mind. Typically, if you see the digital transformation projects or any project for that matter you work on for last several years, they involve cloud services. Cloud like Amazon, GCP and Azure, and also products like Kafka and Cassandra and other distributed databases or Kubernetes now that everyone uses that. And I was like everyone using it or started using it back then, 2017-ish. And I was trying to learn all of these things, struggling my way through it. And at the same time, there was an interesting work that a team in our Pune office was doing. And I just happened to work with that team to help them out. And this was for writing software for a large optical telescope called 30-meter telescope. And a lot of problems that they had to solve, essentially keep data distributed and distributed copies of data in sync, have different telescope subsystems coordinate and work towards some task. All those I thought were similar to what I was learning about the systems like Kafka or cloud services. But for this 30-meter telescope thing, the challenge was that they had to build things from scratch. And so there was a need to understand all these things in little more depth so that you are confident that the decisions that you are taken are right. And at that time, we actually started, I started going a little more deep and trying to understand all these things. Things like Paxos, for example, or things like Lamport clock. And when I went to books, the books were very theoretical, I thought. They explain a concept, they talk about asynchronous systems and synchronous systems, and even things like Lamport clock or Paxos. But there is always some mathematical abstraction or description in terms of pseudocode. And you don't really see how Lamport clock is used in practice. So there was that huge gap that I struggled with. And so what I decided was to really go to open source code bases. And that's the beauty of open source. I think there is so much code available for you to look at. So I started going through Kafka's code base and Cassandra's code base and various other code bases. And then I figured out that I could connect dots. What I was reading about and what I could see in the code, I could connect those dots. But there were also some gaps. I mean, what was explained in the book versus what was actually implemented. There were some gaps. So what I decided to do was like Kafka as a whole is a big system, right? I mean, it does so many things. So if I focus on maybe step by step, if I have to build something like it, what all decisions I need to take and what all implementation, what all different components I need to code. So I started doing that. So I coded my own miniature Kafka. I coded my own miniature Cassandra. And I made sure that the code is not toy code. I mean, it resembles what I actually see in production code of Kafka or Cassandra or similar tools. And I mean, that worked pretty well because then I had like real code to look at when I was talking to people. They also had real code to reason about. And that worked pretty well on that 30-meter telescope project. I did a couple of workshops using this technique, like just don't talk about distributed system theory, but let's build Kafka-like thing in a few days. And this approach of like tackling one problem at a time, and then next problem, and then weaving multiple things together, and then you have this big system, which looks complex. If you look at it like as a whole, it looks complex, but once you focus on like one thing at a time, it's a bit easier. And then I happened to talk to Martin about what I was doing, and Martin has done this kind of thing in the past with various systems, like his Patterns of Enterprise Architecture book. I think is a similar thing done to the world of object relational mapping frameworks. So he liked the idea, and he actually suggested me to write patterns, because what I was the small components and small problems I was trying to solve one at a time. He thought that can be very well explained as a pattern, and that's where it started. So that's when around 2020, start of pandemic, I started documenting these patterns, and in last 3 years, I think we got to a stage where we had enough patterns to maybe explain something like Kubernetes or Kafka, and then we decided to compile it into a book.
It was helpful, I guess, that we were locked down in a lot of places and you were stuck at home, I imagine, and had a lot of time on your hands to write.
Lockdowns during pandemic, I think that gave me a lot of time to work on these things. Yeah.
Did you find it was a difficult transition from writing code to communicate to other people, to writing in English, to describing these things in English in a concise way? Did it take you a while to kind of get into the pattern of writing patterns?
No, actually, having code in front of me or in front of people while I explain things in English, that actually worked pretty well, and I think that's one of the beauties of patterns approach. I think that patterns. I mean, you have some well-defined names, like Lamport clock is a well-known name, or a write-ahead log is a well-known name, or even Paxos is a well-known name. But when you read just English with, let's say, a pseudocode or some abstraction, you need to imagine things, and then you make some vague impressions in your mind of what that thing really is. Now, as opposed to that, when you have real code in front of you, which highlights what Paxos looks like or what Lamport clock looks like, it's actually very easy. And so even for me, writing was easy after the code and some examples were done. So the hardest part was to getting that code that shows the essence of a particular pattern, and then writing about that around that was an easier thing.
I think that's interesting. I think it reflects kind of the approach to technology that we have at Thoughtworks, which is you can talk all you want, about your opinions, but until you write the code, you don't actually know. And the, opinions walk, code talk. And I think that's the way we try to ground things usually in practice. And I think that's an interesting way to approach it.
Yeah. I mean, Martin often calls, and I like his sentence that he says code is like mathematics of our profession, because when you write code and execute it, you cannot cut corners. When you are drawing on the board or writing about something, I mean, you can cut corners, and that's true about a lot of books on distributed systems as well. That even if the focus is to prove that something works, there are certain assumptions, or there are some, and those assumptions might fail in practice, or you can very well ignore some of the assumptions that are out there. And if you're not aware of those, you can run into real issues in production.
Yeah, I wonder how many other people have been through this experience. I know I did years ago when I first naively tried to start building distributed systems, and then ended up reinventing a lot of the things. I know that I pulled this book out because this was a really influential book for me. I don't know if you can see it. It's Jim Gray's book on transaction processing. Yes. Like that. I was so relieved when I found, somebody's actually documented how these things work, and I think your book is probably going to be similar for people. It's ironic that we live in a world where distributed computing is ubiquitous, right? I mean, with the cloud, everything is distributed, and yet there are so many abstractions and tools and open source frameworks that remove a lot of the details of that away from us, that even though we're using it more, I think developers who are just starting in this probably learn less about it because they don't have to actually build it themselves. Do you try to get beyond those abstractions?
Oh yeah. I mean, that was one of the main goals, that to go beyond abstractions and to show real code. And I really liked when I saw Jim Gray's book that you showed, because that was the book that was something that I wanted to do with distributed systems. It's sad that Jim Gray's book came in 1990s, and it's excellent because it does the same thing that I wanted to do with distributed systems. It doesn't leave things to imagination. It gives you very concrete things that you observe in systems at the code level, so you can read and be sure that this is something that you can expect. For even things like, as I said, so book has 4 broader sections. One bigger chunk is about replication. One is about how you manage time in distributed systems, and then how you manage a cluster. Servers communicate with each other. Those are the broad sections. But something as obvious as replication has a lot of complexities, and I think it's not obvious to developers when they read about replication, because replication, the term is, at least people think that it's a well understood term, where in practice it is really not, because replicating data on multiple servers and then making sure that they agree on the data that's replicated, it requires consensus, and so truly, systems which give you that kind of a guarantee really need to implement something like Paxos or Raft. And now you see that most systems or most data systems, including Kafka and all the newer databases which implement this replication, they implement Raft or Paxos as that replication mechanism. But having concrete understanding of what goes on in something that's at least perceived to be obvious is important. I think in the book I try to go into the details of at the implementation level how this replication mechanisms work.
So one of the things I was wondering about, a feature, if you will, of patterns is that you can talk about when they are applicable. And given the fact that some of the things that you're talking about are somewhat fundamental notions, there are, for example, lots of ways you might decide to use distributed time. And so as you were looking at these different code bases, did you mostly run across essentially the same implementations, or were there times when there might have been different implementations for one of these more fundamental constructs that you were able to examine?
Yeah. So one of the, I think, again, the strengths of patterns approach is you look at multiple things, and the rule of three is generally followed, that you look at least three things before you call something as a pattern. And then there is this concept of similarity. So in various systems, the implementations are similar but not exactly the same. And patterns allow you to document what similar thing is across these systems, and there can be variations that you then document as well. So about the replication and distributed time, as I said, if you consider replication, that I said is complicated than what people think it is. And if you consider raft implementation that's used in products like CD or more modern NewSQL databases, and you look at Kafka's replication protocol, there are similarities, but they are not exactly the same. For example, the way Kafka maintains high watermark and Raft has something called as a commit index to differentiate between what is a stable portion of the log and what is the portion that you are not sure about. It is same. The way they use something that I call as a generation clock, or Kafka called it epoch, and Raft calls it a term. But that's really to detect if there are stale leaders out there which are trying to cut across your new leader. And those things are similar, but not exactly the same. So what I have tried to document is the similar portions with differences documented as well. And for distributed time, it's similar. I think so. Lamport clock is very, very, very fundamental, and all key value stores use it essentially to order, to detect ordering of writes. But what you see in practice is a variation of that Lamport clock called hybrid clock that's used, because Lamport clock, as it's documented, is just a simple integer counter that you use, and then you pass it across all your messages, and they're stored with the values that are stored as well, to make sure that you detect which writes happen before other. But in practice, in the data world, you typically will like to have real date time and real timestamp attached to these values to detect which values are written earlier and later. And so this Lamport clock technique is used along with system timestamp. So you use that counter, but a system timestamp as well. And I'm saying system timestamp, but this is another thing that's not well understood. I think that different servers, when they use system time, the time that your machine gives you or the server gives you, there is no guarantee that those will be in sync. And that's a big problem in practice, because then you can have issues where your Newer writes, if they are assigned an older timestamp or a lower timestamp, they can get overwritten by something that was written before but was assigned a higher timestamp, and that's a big big challenge. So most practical systems, they combine this Lamport clock technique along with this system timestamp, and that's the hybrid clock technique that's used, and that's used in a very similar way across all data systems. Like MongoDB uses it the same way, CockerDB uses it the same way, UBabyteDB uses it the same way. Other advantage of again the patterns approach is that if you see all these systems, they are written in different programming languages, from Scala to C++ to Erlang to Golang to Rust, but the broader implementation structure of all these things, it remains the same, even if the language of implementation differs.
It's interesting. I see some kind of parallel between the work that you've done and the Jepsen project in verifying perhaps the claims of some of these systems and actually digging into the details to see how they really work. Because we hear there's so many, even with open source, there is so many claims made that are a little bit superficial that don't really go into these details. I'm curious if you found any contradictions when you were digging into the code, or errors, or things that didn't quite work the way they were advertised.
Yeah, I mean, not contradictions, but things that are omitted from the descriptions, like Paxos, for example. It's very, very popular replication algorithm or consensus algorithm. And there are some obvious things like, Paxos stops at the point where it says that, okay, multiple nodes now agree on one value or one command to execute. And then one of the nodes knows about it. But then how do you make sure that all the nodes know about it? Because in a distributed database, for example, it's not enough for one node to know about it. You need to have all the replicas to remain consistent, or to have the same data. And Paxos doesn't talk about that. I mean, what's called as full replication, that you make sure that everyone finally reaches same state. Paxos doesn't talk about that. And this looked like an obvious question that anyone would ask. And I was searching in implementations. There are some implementations of Paxos which are popular in academic circles, but they don't solve this problem, and they don't even talk about this problem. And it's really fascinating and surprising that it required a new PhD thesis, that's Raft, which clearly talked about that. Okay, this is also a problem that you need to solve along with basic consensus, and it gives you the complete description of that. Or there are, people which or the implementations which claim that they use Paxos, like Cassandra. They use their own extension to solve this particular issue. And that extension works, I think, but that's an extension to what is proven by Paxos. So there were things like that. So that's the advantage that I found while working on this, that you get these questions, and even when these questions that people hesitate to talk about, they are real questions that can bite you in your production implementations. Like with Raft, for example, Raft's leader election and any Paxos implementation, for example, can go into live lock. All the nodes, they just keep on tripping the leaders and just go into a phase where there is leader election happening with no real work that any node is able to do. And this is a real problem. Even if you have good Raft implementations, they can go into this problem. And like a couple of years back, I think there was an outage in Cloudflare system. It was, I think, a 6-hour long outage, and this primarily happened because of this live lock in Raft implementation of its CD. And some of these things, I mean, this can happen in your Kafka cluster or Kubernetes cluster, which use this Raft algorithm. And some of these loopholes in these implementations, you at least need to be aware of that. Okay, something like this can go wrong, and even if the documentation doesn't say aloud that this can go wrong, this can go wrong in practice, or even things like I talked about hybrid clock, and with hybrid clock. Or the basic characteristic of Lamport clock, that you only get partial order. And when I say partial order, if there are two independent writes happening on two different nodes, you cannot really figure out which happened first and which happened later. It's only when two nodes are talking to each other for writing to the same key, let's say, you can detect the order. But if there are independent keys written on independent servers, you can't detect the order. And for that, and Google has their own infrastructure with something called as true time. But open source implementations, which can be deployed on a data center or different cloud settings than Google, they don't have luxury of this true time. And then what they need to do is they need to assume what can be the maximum clock drift or clock skew across servers. And they use, and I have documented this as a pattern called as clock bound wait. That you just wait to make sure that the timestamp at which you are writing, all the other servers have actually reached that timestamp before you make that write visible to others. And some of this are subtle things. So if these assumptions go wrong, that the maximum clock skew, if you assume to be, let's say, 200 milliseconds, and in reality it's 500 milliseconds or more than that, which can very well happen, then you can see those writes done in the opposite order to watch what they really are done. So these kind of things, I think you will get to know, or at least question some of the documentations.
Yeah.
Well, and I think that speaks to the whole purpose, though, of writing a book that lays out not just the pretty abstraction, but the reality of the implementation details, because you're not going to run across a problem most likely with the pretty abstraction. You're going to run into a problem in production when reality hits the code, and it is truly amazing how often people will use libraries and system tools like this without really understanding what's under the hood. And you can kind of understand that because, maybe it works 99% of the time. And so it's a lot of work to do what you've done over the last 3 years to really understand these things. But I do think that's the role that this book has, is it provides the mechanism where you can get it, it's kind of the middle ground, if you will, between the nice, pretty abstraction and somebody having to troll through the entire commit history of Kafka to figure out how it works. This is a nice middle ground.
Yeah, absolutely. I think, and I mean, one of other observations I had when I started my career, I mean, just to relate to the times we are now, to the times back in late 90s, I think. So as an industry, I think when we don't know how to make sure that people understand certain concepts, people fall back on certifications. So you see the times where everyone is asking for Amazon certifications and GCP certifications and stuff like that. because we don't know. I mean, we don't know how to make sure that people understand how these systems work. And understanding these patterns or the basic principles of how, for example, Amazon builds the services that it provides, it gives you a good way to understand broader spectrum of systems. So you need to don't need to do individual certifications, because those are surface level things that you will get to know with that. So I think something like this will help solve or bridge that gap that we are facing today.
There's so much that a software engineer has to know today, and what should we expect them? What of this material, or how deeply into this material do you think people should have to delve just to reach the lowest bar in qualification to work in cloud or with Kafka or something?
Right. So in the book, we actually have divided it into two parts, and that's very typical of Patton's books. I think the first section just gives the overview of the patterns, and it talks about all the problems and just a cursory view of how a particular pattern solves it, and then how they link together. So to start with, I think it's easier to just get this broad view of what things can go wrong and how different implementations tackle it. And then when you are working on something and maybe need to deep dive into one specific thing, then you can go and read a pattern that talks about that thing. So that's the best way to use this, I think. Yeah, because that's the another aspect of Patton's book as well. I mean, you can't read it end to end. It's a hard thing to read end to end. So you have to focus on one thing and read it.
Given our limited attention spans now, I actually like that. I like that I can pick it up, and absorb one thing and then put it down till the next time. Yeah.
So we did a podcast about 3 years ago when you first started writing. What would you say is the major change in the things that you've talked about from that first podcast to today? Was there one big section that you wanted to finish and that's been done in that time?
Oh yeah, I mean, two major things. I think I've documented patterns of distributed time. That's a major chunk, and also detailed out things like backsource and replicated log, which are foundational to any consensus mechanism used for replication. So those two are the major changes since last time we talked.
And have you soured on ever writing a book ever again?
Yeah, possibly. I mean, after some break that I need.
Will you be doing any workshops or?
Yeah. So I'm doing workshops for Aurelie, which I was doing once a quarter, I think, while I was working on the book. But I will do more of those in future, I think.
I'm sure there's going to be an audience for it. It'd be a big demand for it. Like some of the conferences that I've been to, I think people would be really interested. Anything else you wanted to say, Unmesh?
Yeah, no, just read book and send me questions if you
okay.
And I hope, one of my hopes is that people will get questions and openly start talking about obvious things that might be missing from popular implementations. So I like to use use this term wise fool. Wise fool is someone, the story of emperor's new clothes. And it's the kid that says that, okay, emperor is wearing no clothes. So when everyone was hesitating, So we need more of those talking about obvious things and discussing them aloud.
Yes. Yeah, I agree. Yeah. Well, once again, congratulations. I think this is a huge accomplishment, and you should be very proud of yourself for having got through that. And I'm looking forward to reading more of the book. I've read some of the patterns, but I'm looking forward to reading more of them. And best of luck.
Thank you, Scott. Thank you, Rebecca.
Thanks for joining us.